Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1564, put boxes into the warehouse. This problem challenges us to optimize the placement of boxes within a constrained warehouse setup. It's a fantastic exercise to sharpen your problem-solving and algorithmic skills. Let's dive in. In this problem, we are tasked with organizing boxes into a warehouse under specific constraints. We are given two arrays, boxes and warehouse. The boxes array represents the heights of the boxes we have, while the warehouse array represents the heights of the slots available in the warehouse. These slots are arranged in left to right order, and a box can only fit into a slot if its height is less than or equal to the height of that slot. Importantly, the boxes can be rearranged in any order to maximize the number of boxes we can place into the warehouse. The goal is to determine the maximum number of boxes that can fit within the constraints. For the input, the boxes and warehouse arrays can each have up to 10 to the power of 5 elements, and the heights of both boxes and slots can range from 1 to 10 to the power of 9. The output should be an integer representing the maximum number of boxes that can fit into the warehouse. Let's consider an example to make this clearer. Suppose the boxes array is 4, 3, 4, 1, and the warehouse array is 5, 3, 3, 4, 1. After rearranging the boxes as 1, 3, 4, 4, we can fit the box with height 1 into the last slot of the warehouse with height 1. Next, we place the box with height 3 into the third slot with height 3. Finally, we place the box with height 4 into the first slot with height 5. This allows us to fit a maximum of 3 boxes into the warehouse. The output for this example would therefore be 3. Now, let's look at another example. If the boxes array is 1, 2, 2, 3, and the warehouse array is 3, 4, 1, 2, we can rearrange the boxes as 1, 2, 2, 3. First, the box with height 1 can be placed into the third slot of the warehouse, which has a height of 1. Then, the box with height 2 can be placed into the fourth slot with height 2. Finally, another box with height 2 can be placed into the first slot with height 3. In this case, the maximum number of boxes we can fit is 3. The constraints of the problem further highlight that we need an efficient algorithm, as both arrays can be very large, up to 10 to the power of 5 elements. Additionally, we must handle edge cases, such as when no boxes can fit, when all boxes can fit, or when the number of boxes exceeds the number of slots in the warehouse. These considerations emphasize the importance of balancing efficiency and correctness in our approach. To solve the problem of maximizing the number of boxes that can be placed into the warehouse, we need to carefully navigate the constraints. A box can only be placed in a slot if its height is less than or equal to the slot's height, and placement must proceed sequentially from left to right in the warehouse. This means we can't skip slots or rearrange the order of placement. The challenge lies in finding the most effective way to fit as many boxes as possible while respecting these rules. To address this, we'll evaluate multiple approaches, each with its own advantages and trade-offs, to determine the best strategy for this problem. One approach we could consider is the brute force method. In this approach, we check every box against each warehouse slot, placing a box if it fits and then removing it from the list of available boxes. While this method is conceptually simple, it's computationally expensive. Each comparison takes time, and with n boxes and m slots, the total time complexity becomes n squared, for larger input sizes. Another approach is an optimized greedy strategy. Here, we start by sorting the boxes in ascending order of height, which allows us to focus on placing the smallest boxes first. We also preprocess the warehouse to create an effective height array, ensuring that each slot accounts for the minimum height constraint as we move from left to right. This preprocessing step eliminates the need for repeated height checks later. With this setup, we place the smallest available box in the first slot that can accommodate it. This method is significantly more efficient, with a time complexity of n log n plus m. Finally, there's the option of using a priority queue, or min-heap, to dynamically select the smallest box for each slot. While this avoids sorting the boxes up front, it adds additional memory overhead and complexity for maintaining the heap. The strategy we chose to solve this problem is the greedy approach, as it offers the best balance of efficiency and simplicity. By sorting the boxes and preprocessing the warehouse, we streamline the process of determining which boxes fit into which slots. The key insight here is that smaller boxes are inherently more flexible, and prioritizing them ensures that we maximize the number of placements. Additionally, pre-processing the warehouse to reflect the minimum height at each slot simplifies our logic and reduces the need for redundant checks later. Together, these steps allow us to achieve a solution that is both intuitive and highly efficient, with a time complexity of n log n plus m. This combination of sorting and pre-processing ultimately minimizes the problem's complexity while adhering to all constraints. When comparing the approaches, it's clear that each has its own strengths and weaknesses. The brute force method is straightforward but becomes impractical for larger inputs due to its n squared complexity. The priority queue approach, while an improvement in some ways, introduces additional space overhead and does not outperform the greedy approach in time complexity. The greedy approach, on the other hand, strikes the perfect balance. It provides optimal performance with minimal space usage, making it the most practical and efficient choice for this problem. By leveraging sorting and preprocessing, we can achieve a streamlined and effective solution that adheres to all constraints while maximizing the number of boxes placed in the warehouse. The problem asks us to maximize the number of boxes we can place into a warehouse. The heights of the boxes are given in an array called boxes, and the warehouse is represented as another array called warehouse. Each element in the warehouse array indicates the maximum height a box can be to fit in that position. Boxes can only be placed sequentially from left to right, which means once we place a box in a slot, we move to the next slot to the right. To approach this problem, we need to consider a few important insights. First, sorting the boxes by height is crucial. By placing the smallest boxes first, we can make the best use of the smaller slots, leaving larger slots available for bigger boxes. Second, the warehouse array often has heights that decrease as we move from left to right, but there can be local increases that complicate placement. To simplify the problem, we pre-process the warehouse array to create a usable array, where each slot reflects the tightest possible height constraint from left to right. Finally, a greedy approach works well here. By sorting the boxes and iterating through the warehouse, we can place as many boxes as possible in the smallest available slots. This ensures we maximize the number of boxes placed efficiently. Now, let's break the solution into clear steps. First, we pre-process the warehouse array to create the usable array. This involves iterating through the warehouse heights and ensuring that each slot reflects the minimum height constraint from the start up to that position. For example, if the current slot's height is greater than the previous slot's height, we adjust it to match the previous slot's height. This pre-processing guarantees that each slot in the usable array is constrained by all the slots to its left. Next, we sort the boxes array in ascending order. By doing this, we can focus on placing smaller boxes first, which is key to maximizing placements in constrained slots. Once pre-processing and sorting are done, we move to placing the boxes. For this, we use two pointers, one, B, to track the current box and another, W, to track the current warehouse slot. As we iterate through the usable array, we check if the current box fits in the current slot. If it does, we place the box and move both pointers forward. Otherwise, we simply move the warehouse pointer to the next slot. This process continues until either all boxes are placed or we run out of warehouse slots. At the end, the value of the box pointer, B, gives the total number of boxes successfully placed. Efficient data structures play a key role in this solution. The usable array simplifies placement by allowing O1 access to the pre-processed warehouse heights. Additionally, the use of two pointers, one for the boxes and one for the warehouse, ensures that we process both arrays efficiently during placement. This approach minimizes the need for nested loops or additional complexity. Let's analyze the time and space complexity. Sorting the boxes array takes n log n, where n is the number of boxes. Pre-processing the warehouse array takes m, where m is the number of warehouse slots. The final placement phase, which involves iterating through both arrays with two pointers, takes n plus m. Combining these, the overall time complexity is n log n plus m. For space complexity, we use m extra space for the usable array, making the solution quite memory efficient. To understand this better, consider the given example. Suppose we have boxes equals 4, 3, 4, 1, and warehouse equals 5, 3, 3, 4, 1. First, we pre-process the warehouse to create the usable array. Starting from the left, we ensure each slot reflects the tightest height constraint from left to right. This results in usable equals 5, 3, 3, 3, 1. Next, we sort the boxes array, which gives us boxes equals 1, 3, 4, 4. With these preparations complete, we move to placing the boxes. To place the boxes, we begin with the smallest box, which is 1. This fits in the last slot of the usable array, so we place it there and move both pointers forward. Next, we take the box with height 3, which fits in the second to last slot of the usable array. Again, we place it and move both pointers forward. Then, we take the first box with height 4. This fits in the first slot of the usable array, so we place it there and move the pointers forward again. At this point, we have no more slots available for the second box of height 4 because the remaining warehouse slots have heights too small to accommodate it. Thus, the placement process ends here, and the total number of boxes placed is 3. This example highlights how sorting and pre-processing work together to maximize the number of boxes placed. By ensuring each step is efficient and systematic, we can handle even larger inputs with ease. Let's also consider some edge cases. If the boxes array is empty, the result is 0 since there are no boxes to place. Similarly, if the warehouse array is empty, the result is also 0 since there are no slots available. If all boxes are too large to fit in any slot, or if all slots are too small, the result is again 0. Finally, if multiple boxes have the same size, sorting ensures they are placed in sequence, avoiding conflicts and maximizing placements. Here's the Python implementation of the solution. We start by pre-processing the warehouse array to create the usable array, where each slot reflects the minimum height constraint from the start up to that position. Next, we sort the boxes array in ascending order. Then, we use two pointers, one for the boxes array, B, and one for the warehouse array, W, to place the boxes. If a box fits in the current slot, we increment both pointers. Otherwise, we move only the warehouse pointer forward. Once the process is complete, we return the value of the box pointer, B, which represents the total number of boxes placed. This implementation is efficient and adheres to the steps discussed earlier, ensuring clarity and correctness in solving the problem. Here, we start by defining the maxBoxesInWarehouse function inside the solution class. The first step is to sort the boxes array in ascending order. This allows us to try placing the smallest boxes first, which is important for optimizing the placement given the warehouse constraints. Next, we adjust the warehouse array to account for the leftward constraints. As we iterate through the warehouse, each position is updated to the minimum of its current height and the height of the position to its left. This ensures that each position represents the maximum height a box can fit, considering the leftward restrictions. After this pre-processing, we initialize two pointers, box_pointer, starting at the smallest box, and warehouse_pointer, starting at the rightmost position in the warehouse. We also initialize a count variable to keep track of how many boxes have been successfully placed. With these variables set up, we move into the while loop, which continues as long as there are boxes to place and available positions in the warehouse. Inside the loop, we check if the current box can fit into the current warehouse slot. If it can, we increment the count of placed boxes and move the warehouse pointer to the next slot on the left. Regardless of whether the box was placed or not, we always move the box pointer to try the next smallest box. Finally, after exiting the loop, we return the count variable, which represents the total number of boxes successfully placed into the warehouse. This completes the implementation. The function efficiently handles the constraints by ensuring the warehouse heights are pre-processed to reflect realistic placements and by using a two-pointer approach to iterate over the boxes and warehouse slots. This approach ensures that smaller boxes are prioritized for placement, and the solution is achieved with minimal computational overhead. Here, we start by importing the necessary utilities and defining our solution class. The goal is to determine the maximum number of boxes we can fit into the warehouse while respecting its constraints. First, we sort the boxes in ascending order, as smaller boxes are easier to place and can fit into tighter spaces. Next, we adjust the warehouse heights to account for leftward constraints. This means that at each position, the height is updated to the minimum of its current height and the height of the position to its left. This ensures that the warehouse heights accurately represent the maximum height a box can fit, moving left to right. Now, we set up 2 pointers, one for the smallest box, starting at index 0, and another for the rightmost warehouse slot, starting at the last index. We also initialize a count variable to track how many boxes have been successfully placed. Then, we use a while loop to attempt placing boxes into the warehouse. If the current box fits in the current warehouse slot, we increment the count and move the warehouse pointer left. Whether the box fits or not, we always increment the box pointer to check the next box. Finally, after the loop finishes, we return the count of boxes that were successfully placed into the warehouse. This count represents our solution to the problem. The logic ensures that we maximize the number of boxes placed by prioritizing smaller boxes and working from the rightmost warehouse slot backward, while respecting the height constraints at every step. This efficient approach leverages sorting and 2 pointers to achieve an optimal solution with minimal complexity. To solve this problem, we start by sorting the boxes in ascending order so that we can try to fit the smallest box first. For the given input, the sorted boxes are 1, 2, 3, 4. Next, we adjust the warehouse heights to ensure that each position reflects the maximum height a box can fit, considering the leftward constraints. This means that the height of any position cannot exceed the height of the position to its left. We process the warehouse from left to right, updating each position iteratively. After making these adjustments, the updated warehouse remains 5, 4, 3, 3, 2, as no changes were needed. With this setup, we initialize 2 pointers, one pointing to the smallest box, starting with box_pointer equals 0, and the other pointing to the rightmost warehouse slot, starting with warehouse_pointer equals 4. We also initialize a count variable to 0, which will keep track of the number of boxes successfully placed into the warehouse. Now, we begin placing the boxes into the warehouse from the rightmost slot, moving leftward. The smallest box, 1, fits into the rightmost slot of height 2. We increment the count to 1, move the warehouse_pointer to the next slot to the left at index 3, and advance the box_pointer to point to the next smallest box, 2. Box 2 fits into the slot of height 3. Again, we increment the count to 2, move the warehouse_pointer left to index 2, and advance the box_pointer to 3. Similarly, box 3 fits into the slot of height 3, so we increase the count to 3, move the warehouse_pointer left to index 1, and proceed to box 4. Finally, box 4 fits into the slot of height 4, bringing the count to 4. At this point, all boxes have been placed, and the final output is 4. In this example, we are given larger boxes and a smaller warehouse. The input boxes are 6, 5, 4, 3, and the warehouse heights are 4, 3, 3, 4. We start by sorting the boxes in ascending order, resulting in 3, 4, 5, 6. Next, we adjust the warehouse heights to ensure that each slot respects the leftward constraints. Processing the warehouse from left to right, the updated heights are 4, 3, 3, 3. This ensures that each position reflects the maximum allowable height for a box. We then initialize the box_pointer to 0, pointing to the smallest box, 3, and the warehouse_pointer to 3, pointing to the rightmost warehouse slot of height 3. The count variable is set to 0 to track the number of boxes placed. We attempt to place the boxes into the warehouse, starting with the smallest box. Box 3 fits into the slot of height 3, so we increment the count to 1, move the warehouse_pointer left to index 2, and advance the box_pointer to 1. Box 4 also fits into the slot of height 3, so we increase the count to 2, move the warehouse_pointer left to index 1, and advance the box_pointer to 2. However, the next box, 5, is too large to fit into any remaining slots, as is box 6. These boxes cannot be placed into the warehouse. The final result is that only 2 boxes were successfully placed, and the output is 2. In the final example, we are given boxes 7, 8, 9, and a warehouse with heights 5, 4, 3, 2. After sorting the boxes in ascending order, we get 7, 8, 9. Next, we adjust the warehouse heights to ensure the leftward constraints are satisfied. This results in the updated warehouse heights 5, 4, 3, 2. We initialize the box_pointer to 0, pointing to the smallest box 7, and the warehouse_pointer to 3, pointing to the rightmost warehouse slot of height 2. The count variable is again set to 0. As we try to place the boxes, box 7 cannot fit into the slot of height 2, so we move to the next box. Box 8 is also too large for any slot, as is box 9. None of the boxes can be placed into the warehouse. The final result is that 0 boxes were placed, and the output is 0. To evaluate the time complexity of the solution, we can break it into 3 primary operations. First, we sort the boxes array in ascending order. This sorting uses Python's built-in sort function, which operates with a time complexity of O, m** log m, where m is the number of boxes. Next, we adjust the warehouse array to ensure that each position reflects the maximum height a box can fit, given the leftward constraints. This adjustment involves a single pass through the warehouse array, iterating from the second element to the last, resulting in a time complexity of O, n, where n is the length of the warehouse. Finally, using the two-pointer technique, we attempt to place each box into the warehouse. In the worst-case scenario, each pointer traverses its entire array, leading to a time complexity of O, m plus n. When we combine these steps, the overall time complexity becomes O, m** log m, plus O, n, plus O, m plus n. This expression simplifies to O, m** log m, plus m plus n, but since sorting dominates the asymptotic behavior, the final time complexity of the algorithm is O, m** log m, plus n. Now, looking at the space complexity, we start by considering the input storage. The boxes array and the warehouse array occupy O, m, and O, n space, respectively. However, these are inputs and do not add to the algorithm's extra space usage. The warehouse array is updated in place to reflect the adjusted heights, meaning no additional space is allocated for this step. Furthermore, the algorithm relies on a constant number of variables, 2 pointers, box_pointer and warehouse_pointer, and a counter, count, all of which together require only O1 space. No auxiliary data structures are used, so the overall space complexity is O1. To further understand the efficiency of this solution, let's compare it to a brute force approach. In a naive method, we would attempt to place each box into every possible slot in the warehouse, checking all combinations. With m boxes and n slots, this results in a time complexity of O, m** n. In contrast, the optimized approach significantly reduces this overhead by combining sorting with a two-pointer technique. By sorting the boxes array and leveraging the constraints of the warehouse array, we reduce the time complexity to O, m** log m, plus n. This is a substantial improvement, particularly for large inputs, where sorting is far more efficient than exhaustively iterating over all combinations. Now, let's consider the best, worst, and average cases for the algorithm. In the best-case scenario, all boxes can be successfully placed without skipping any slots in the warehouse. Even in this case, sorting and adjustments are always required, so the time complexity remains O, m** log m, plus n. In the worst case, no boxes can be placed due to constraints, but the algorithm still processes all elements, maintaining the same time complexity. On average, we expect some boxes to fit while others are skipped, yet the overall time complexity does not vary, remaining O, m** log m, plus n. From a mathematical perspective, sorting dominates the runtime because O, m** log m, grows faster than O, m plus n, as m becomes large. With no additional data structures used, the space complexity consistently remains O1. This optimized solution effectively balances efficiency and simplicity, making it a robust choice for handling large inputs while outperforming naive methods through strategic use of sorting and two-pointer traversal. When solving this problem, there are a few common mistakes to watch out for. First, sorting the boxes in descending order of height might seem logical, as it could appear to prioritize larger boxes. However, this can lead to issues because smaller boxes are more versatile. They can fit into tighter spaces that larger boxes cannot. Next, it's crucial to adjust the warehouse heights properly. The warehouse slots should reflect the minimum height constraint as you move leftward. If this step is overlooked, the placement logic will fail because the constraints won't accurately represent the warehouse configuration. Another mistake is attempting greedy placement without sorting the boxes first. If smaller boxes are processed after larger ones, they might be blocked, resulting in suboptimal placements. Lastly, there's often confusion about index alignment, whether to process the warehouse from left to right or right to left. Misunderstanding this alignment can lead to errors in both the logic and the placement process. Inefficient implementations are another issue to consider. For instance, solutions that check every box against every warehouse slot will have a time complexity of n squared, which is not scalable for large inputs. To address this, sorting the boxes and using a two-pointer strategy is essential for efficiency. Looking at the bigger picture, this problem is a classic example of a two-pointer strategy paired with sorting. Sorting ensures that the boxes are placed optimally, while the two-pointer technique allows you to traverse both the boxes and the warehouse slots efficiently. Adjusting the warehouse height array to reflect left or right minimum constraints is another key insight, as it simplifies the placement checks. For interviews, be prepared to discuss variations of this problem, such as handling multiple warehouses or introducing additional constraints like weight limits, since these could test your ability to adapt the core strategy. This problem is also closely related to various other LeetCode problems. For example, in LeetCode 135, Candy, you adjust an array based on constraints, a concept that parallels adjusting the warehouse heights here. Another related problem is LeetCode 881, Boats to Save People, which uses sorting and a two-pointer strategy to ensure optimal placement. LeetCode 763, Partition Labels, focuses on dividing a structure into optimal segments, and LeetCode 1029, Two-City Scheduling, involves sorting and greedy placement to minimize costs, which aligns with the approach used in this problem. Additionally, when considering alternative approaches, a brute force solution might be the simplest to implement. This involves trying every box for every warehouse slot, but it comes with a high time complexity of n squared, making it impractical for larger inputs. On the other hand, using a two-pointer method with sorting is far more efficient. Sorting the boxes in warehouse slots first reduces the problem complexity to n log n, and the two-pointer technique ensures that you can handle placements optimally while managing edge cases carefully. Finally, there's an uncommon but interesting approach involving dynamic programming. With this method, you could track the maximum number of boxes that can be placed for each warehouse slot. While this approach has a time complexity of n squared, it might be overkill for the current problem, as simpler strategies like sorting and two pointers are sufficient. However, dynamic programming could be invaluable for solving more complex variations of this problem, where additional constraints or dimensions need to be considered. Understanding this approach adds another tool to your problem-solving arsenal, allowing you to tackle more advanced scenarios effectively. Great job on completing this problem. We've summarized the key points, including the algorithmic approach and takeaways. Remember, sorting and greedy strategies are powerful tools in optimization problems. Keep practicing, and don't forget to check out our other problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!